Hey, so this is a screencast video series that I'm doing, and the purpose of doing this is to try to build TensorFlow. We're gonna start coding this in C++, and then gradually build wrappers around these C++ APIs and then call them through Python. So the first topic of this first lecture is about building the tensors that TensorFlow has. So a brief overview of TensorFlow and how it works is you have something what is called as a computational graph. Computational graph, right? Computational graph, and so this computational graph consists of nodes and edges like any other graph, but the nodes here are operations. So these operations can be, a multiply operation or an add operation, and the edges are what you call are the data, right? So the data flows through these nodes, and that's why the software we're trying to emulate is called TensorFlow. So the tensors, which are the data, they flow through the nodes, which are the operations, and gradually these tensors are change depending on what operation they go through, and then finally you get a result, which is generally, in the case of neural networks, a loss, and then you back propagate through that loss and calculate the partial gradients with respect to the operation the tensors have gone through. And then after you've computed these gradients via back propagation, you then add them to your weights with by multiplying that the gradients with the learning rate or something. So I'm assuming that the listener is familiar with how back propagation and everything works, and the purpose of this screencast is try to code all our ideas that we have in our head, code it out so that they become more robust. So anyway, let's start with something now. Let's build okay, so this is a Python file. Sorry, let's make a right. Let's include iostream. So second, we include iostream. Just use the STT library namespace for now. We'll change that as we include namespaces, because then we'll need to do that. So let's try to envision what we actually want. So one exercise that I go through whenever I'm designing something is just without coding the functionality, just code out what the API of the thing should look like, and that helps me keep on track of what I want to achieve. So anyway, so we want to firstly build an Autodiff library. What is Autodiff? Autodiff is something that TensorFlow and PyTorch use. It's called automatic differentiation. So the way back propagation is done in these libraries is through a Python package called Autodiff. And our first objective is to recreate the Autodiff functionality in C++. So so on Autodiff, what it does is, suppose you have a tensor 1 equal to tensor 2, right? Okay, assuming tensor is an object, let's recreate two more. Okay. Then we want to create a third tensor which just multiplies 2. Actually, we can override that multiplication or operator in C++, and that's what we're going to do in the future. So okay, once you have 3, I just want to back propagate right? And say like in backward propagation, the loss always has a partial gradient of 1, because you just if you're dx by dx, so for example, f is our loss, alright, and f is calculated x into y, right? So we want dx is, we want df by dx and df by dy. So to do that, we first calculate df by df equal to 1, and then we send this one backwards, and so it'll be something like, let's say void backward, and we have something, let's call it int grad, that's your partial gradient that's coming from ahead, and you have, say, operation 1 dot backward. Let's assume operation 1 is a tensor, and backward, let's say grad into operation 2. Let's see, this is a multiplication example, right? And then operation 2 dot backward into grad into operation 1, right? Something like that. So we'll call this backward function recursively until you hit the end, right? And that's how you calculate your gradients. Alright, how do you achieve this API? Say we want to do this, right? So our first order of business would be to create a class called tensor, right? And then we would need something called maybe an integer tensor, right? For the integer data type, say we want float tensor, right? And so on, vector tensor for when we want to do matrix multiplications, right? Something like that. And I was thinking we would need operations. So your graph has nodes and edges. Our edges will be tensors, right? And our nodes will be operations, right? So we can have, let's just call this an operation. So I'm a bit hazy on C++, so it'll be a learning experience for both of us, you the viewer and me, as I look up how to actually overload a class and in basic inheritance and all that stuff. Say we have an operation, then we want a multiply operation, right? Let's overloaded, and maybe we want an addition operation. I think you need these. Let's just keep an integer tensor for now. We'll come back to different vector in tensors and all that after we complete this part. Okay, so what do we want? So we want this. So of course, okay, let's try to figure out. All right. Okay, so let's say everything public for now. We have an integer int1, right? And then the value, then we want int grad, or let's say yeah, in grad. No, let's call it float tensors. Because mostly TensorFlow uses, like, people generally code their networks in 32-bit numbers, which are float values. I've seen some work that uses 16-point precision. That's supposed to be faster because you're doing half the calculations, right? So you can train really big networks using FP16. FP16 data types. Anyway, so we have the value of a grad, and then what we want to do is then we want something called we want a constructor firstly. So it's flow tensor. Right, we want to send in some value. This is default, right? Then we want to send in some int val, so float val. This, I think this is how you do it. We'll check for errors. I'm sure there'll be a lot. Then maybe we want to, okay. How do you do operator overloading? Let's try to do operator overloading. Okay. So I've already looked this up, and what you do here is let's just copy this. I think it's supposed to be really simple. I'm surprised how simple this was. Generally I wasn't expecting it to be because of C++ is very, like, repetition being really complex. Let's call them float tensors for now. Do I want that? Let's call it star. Float tensor. Res maybe. Okay. 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 Let's say this. The image dot something. Let's check again. Do have this small functions. Okay. So example C3, an example operator plus. So you have obj, then you have real. Okay. All right. Okay. Okay. So we have, let's say val here, and let's say float price equal to 3. Let's call it 3. Float price equal to val dot. Let's say. Why do we need a const here? Let's just call them val. Okay, this right? Just call it grad val. Just call it val. We'll figure that out in the end. Let's call this 2. Just to make it. So we're returning 3. for tensor 3.2 no. Right. Okay. This is better. That should do it, right? This looks good, doesn't it? So what we're trying to do is just use this with this. Overloading the operator, right? 1 and 2. All right. Just go. So anyway, let's just see if that works. Let's say cout 3 dot well, I don't know. Yep. Okay, if you have a pointer, then you have to use this thing. If you don't, then you don't, I guess. 1 into 2. Let's say new. Woohoo! New. Let's call this form. Okay. It looks good, I would say. I think it looks good. I don't know why this is expression master arithmetical unscoped enum type. Okay, I don't know what that is. What's that? Make it pen. I don't think that's right, is it? No, what are constant? Yep. I don't know what this is happening. Just let's try. Okay, so to run C++ file, I think you have to make a make file, and then let me just check. Make file. As you can see, I was prototyping all of this in another folder, and I wanted to clean it up for you guys. C-lang. Okay. Anyway, let's bring up the terminal. I'm using Visual Studio Code in case you were wondering what IDE this is. It's pretty good, and you get all these nice extensions so for C++. So you can see I'm getting some IntelliSense support. Make. Okay, do have a make file, right? Make. Should delete this. Make file name also would be. Okay, should work. No targets, no make file found. Forget it. Just go. Okay, 1 into 2. Invalid operands 2 of types flow tensor to binary operator. This. Okay, how do we do this? I'll figure this out offline. I just wanted to tell you guys how the API should look like, so I'll get on with it. So anyway, we'll figure this out, exactly what error this is. I'll show that in the next episode. Anyway, so what we'll have is, maybe we'll have like multiply, right? Void multiply something, maybe, right? And then what we can do is then, create an multiply operation op equal to new multiply operation, right? So we can have like a float, we can have a tensor here, tensor 2, right? Then we can have a multiply operation here, right? Then we can add something like we can add these two and this 2, right? And then we might give this forward operation is, we give it this off, right? And maybe alright, so, and we can have maybe void backward here. So if you ever use PyTorch, you know that there's a forward and a backward thing. So when you have when you backpropagate, you generally get a gradient through which you calculate the partial derivatives. So let's just call the gradient tensor, let's have a separate class, maybe gradient grad, right? Then what we'll just do is we'll store this dot grad, right, for future, for just to do a step function or optimizing function, that's later. But so generally what will happen is, this is this dot while equal to this dot while minus learning rate into grad. This is what happen when you're stepping through a loss function when you're backpropagating. Gradient descent. No, sorry, gradient descent. Sorry, this is gradient descent. So let's just call this backward, and then we will this dot backward of operation dot backward. Let's just send this gradient through, right? We'll send this gradient through, and that will just like if this is not making sense right now, let me try to create an operation, right? Let's try to create an operation which will be let's say multiply operation. Multiply operation, and then we might have, let's say what will go wide backward, let's say. So we get a gradient here, right? And we have, let's say tensor 1, tensor d1, d2, because each generally operation has 2 operands, right? If it's not like a log or something. We need to handle that separately, but those operations which generally have 2 operands, this should work. So this is a multiply operation. So a multiplication, when you're back propagating through a multiplication, is generally called a switcher. So this code will make sense. Let's say t1 dot, let's just call them float tensors. And now, okay, we'll actually get all of this working in the next episode. I need to fix some errors that will take a lot of time, but I'm just showing you how the flow will work of our AutoGrad system, right? t1 dot backward, let's say grad into t2 dot val, something like this. And then we can also have something like t1. This is called a switcher, right? And if you had like an add operation, I'll just show you. An add operation just distributes, so it just distributes this grad. If you had an add operation, say you had everything the same, and then you just remove this, so the grad flows through both operations equally. Right, I'm just wondering if like if I'm doing this, then I'm doing this, does it affect when we're going backdropping, right? I'm just wondering if we need to write some breadth first search kind of thing, where you go through all the edges at the same level, you reach them at the same time, and then you continue on, right? You don't want like a depth first search thing, right? Because that will give you wrong answers, because you'll calculate some gradient values, you'll push it backwards, and then that operand will push it backwards, but maybe there's another tensor on level, if you're talking about level 0 1 2 3 4, when you're backdropping with 0 1 0, level 0 being at the being where your loss was computed. So if one operation goes at level 0 and you backdropping, you go to level 1, you can go to level 2, you go to level 3, and you do, but what if there's another node at level 0 that needs to send its gradient to node 1 at level 1? So you have to have a breadth first search strategy to go through, to backpropagate through everything. So I hope this makes sense. You have a multiply operation, we have like a backward function, and we switch it. The multiply operation is called the switcher, and this is called the distributor. Let's call it the addition function is also called the distributor. And so then we've created something, a class tensor, right? And we have a value, we have multiplication. So this is a multiply. This doesn't make sense. So we can overload the operators with multiplications or additions, right? That should make sense. That's wrong. So we also need to calculate, instead of doing this here, we should ideally be creating like this dot forward operation equal to like operation. It should be a multiply operation, right? get y, right? Do so this should do everything, and then this should actually return new maybe compute, right? Something like this, where compute is like, we'll make this much better, trust me. This is very rough, but as long as we have a clear idea what we want to achieve, so should be t1 dot well into t2 dot well, right? And maybe this could be like backward operation equal to I don't know if you can do this in C++. I don't think so, but if you're coming from a Python background, you can actually send your parameter name in the first term, the second would be just this. So when you do backward here, when you do backward, right? Backward, what happens is a recursive call that goes here. It deposits the gradient, which would be 1 in this case, because you're differentiating with yourself in this case. So the gradient of 1 comes here, and then the backward operation would be like a multiplication. So it comes here, comes into backward 1, you multiply this, and it goes in T1 and T2, which is the float tensors, which are 1 and 2, right? 1 and 2 here, and then you come here, you get the gradient, and then you backward propagate again. But in this case, this would be none, so stop here, like, right? Let's say if this dot backward right, that makes sense. And when you're actually multiplying or forward propagating, so when you multiply, you create a forward operation. Depending on what you do, it's a multiply operation, okay? And then you return after you compute this, right? And you return 3, which would come here. That makes sense, right? I know it doesn't work, but I show you in the next lecture. I'll make this working and explain what I did to change stuff. And then I'm thinking we should have a nice directory structure right here, where you separate all the tensors depending on what their functionality is. We need inheritance here. We need I'm guessing there will be a base class called tensor, which every tensor will inherit from. Similarly for operation, which every operation will inherit from. Then so we'll have that. And then I was thinking, then after handling basic numbers, we'll come to matrices, because everything in deep learning is matrices, right? Matrix multiplication. And I can also show you how to do really fast matrix multiplications, using CUDA. So you put it on the GPU, That's very interesting. And then finally we can train our network, hopefully. So that would be a pretty good achievement, right? Maybe MNIST, let's not get too crazy in the beginning. And what would be best would be, to train MNIST, we should build Python wrappers around our C++ API. So think of, we're building basically a library for computing, for doing our resource heavy computations, and then we just call them through Python, making it very easy. Alright, if you guys want an example of what GPU computing looks like, I can show you what the advantages are. You might not understand the code as such, but so this is the code for like matrix multiplication. So generally you have a global, and then it's not too different, like there's something called blocks and threads. So in the GPU you divide computation in blocks, and each block has a certain amount of threads. So you essentially have your blocks into threads worth of parallel processing going on, and then you get a lot of speed up. So I can just show you here how good a speed up you can actually get. Make file, let's say make files, let's say MECC, right? So instead of G++, we use MECC for CUDA. I don't think we need, okay, let's matrix multiply .cu is the file name. Okay, so we've created our executable. So yeah, let's just run it and see how this performs. So I don't know if you guys can hear it, but the GPU just started. These are big matrix computations. So let's see. Okay, it's bigger. I suppose that must be better. But tile size you can optimize. Throughput, performance is 2x, and this is just a performance of a simple kernel than an optimized kernel. So the simple kernel is simple, just put it on the GPU, don't try to be smart with it. But you can do some algorithmic trade-offs, like you can separate the matrix multiplication into tiles, which results in a 2x improvement. So it's pretty good. Also, if you want to see, there's an image convolution example too, which so right, so that's your speed up. So you get a 98x speed up in image convolution. This is on the CPU, this is on the GPU, so you can see almost 100 times faster, right? So that's pretty good. We will definitely use GPU computing and computing matrices. So I think that's a pretty interesting project, and let me know what you guys think. And if you want any help with something you did not understand, let me know, and I shall address it in the next lecture. Alright, thank you.